Swayam Prabha. Digital India. Educated India.
Today we will continue where we stopped last time. We will look at symmetrical component of some equipment and then go on to use that what we have learnt up to now for unsymmetrical faults. Also symmetrical faults we will have a brief look, and we will see some problems so that the concepts are clear in our mind. So let's start. We will start where we left last time and then move on to other concepts. So we were looking at symmetrical component representation of transformers. We had finished that and looked at symmetrical component representation of synchronous machines also. Now we will move on to sequence modeling of induction machines. So induction machines, unlike synchronous machines, are singly fed machines. That is, there is only AC excitation, no DC excitation. So during a fault, the only thing keeping the rotor rotating is the inertia of the load and the rotor itself. There is no DC field excitation on the rotor, unlike that of a synchronous machine, either a generator or a motor. And the rotor winding is generally short circuited. So whenever whatever fields are there due to the rotor currents will collapse in a matter of a few cycles. So the current contribution of the induction motor reduces and dies out completely after that few cycles. Now this is the reason that the fault contribution from induction motors is sometimes ignored. We can consider it if we want to do a very accurate representation of the fault currents, but even if you ignore it, the loss of accuracy is not too much. If the contribution has to be considered, then only the subtransient value, the xt double dash or the locked rotor value of the impedance needs to be considered, in which case the fault contribution or the short circuit contribution of the motor is roughly of the same order as that of its starting current, which is 5 to 6 times that of its full load current. Also many a times what is done is the contribution of a group of motors is lumped together and considered as one single motor without loss of accuracy. This is how a induction motor is represented in fault studies. After that we have the electrical utility system. Now by electrical utility we mean an equivalencing or a Thevenin equivalent of a utility. We have already considered how synchronous generators are modeled, how transmission lines are modeled, but at the point of fault all those details may or may not be available. You may only have a fault current at that bus, in which case, or a fault MVA at that bus, in which case what is done is it is simply modeled by a equivalent impedance and a voltage source behind that impedance, generally 1 per unit. It is of this form. Okay. So simply an electrical utility system is simply modeled like this. There is some equivalent X or Z that is considered, and this is generally some voltage which is 1 per unit, or could be, if you know the exact voltage at that bus, you can consider that as well, or Z. Okay. In software programs, if you see, it is usually modeled, it's something like this, it's shown like this as a utility system, but in which case you will just have to give it the fault MVA fault MVA has to be fed into the software. What it internally does is models it in this form. Okay. So, we will move on to the next component, which is modeling of the loads. Okay. Loads also like synchronous motors can be ignored when we are calculating faults, and they are mostly ignored when fault calculations are done. However, if you have to be entirely accurate and you need to consider the loads which are some major loads, etc., this is the way to do it. You essentially calculate what are the pre-fault currents, because the load contribution of a static load is only going to be the pre-fault current which is there, so that your calculations are more accurate. So, what is done is it is modeled as a shunt impedance, a positive sequence shunt impedance, which is of this form. Okay. The modulus of the voltage at that bus squared divided by the power in its complex form, which you will get from which you will get the shunt impedance of the load. Okay. And they are added as diagonals to the Y bus. We will see the Y bus formation maybe in the next class. After that, the network element, one network element which is a bit tricky to handle is the series capacitors. What happens is because of the flow of fault current, which could be very high, the capacitors could get damaged. So, in parallel with the capacitor, usually some protective device is provided. Metal oxide varistor kind of device which we have seen earlier in lightning protection, similar kind of device is provided, I am sorry. And when the fault current flows, this actually acts as a short circuit and will protect the series capacitor. So, the series capacitor in effect goes out of the circuit. And the fault current itself would get modified. So, this has to be kept in mind when we are considering series capacitors in fault calculations. Now, after having seen all these elements, let us move on to some actual fault calculation. We will come back to how the calculations are done in a short circuit program a little later, maybe in the next lecture. But for now, we will have a look at calculations of symmetrical and unsymmetrical faults, which we can actually do by hand also. So, first we will have a look at the symmetrical fault, which we discussed a bit in the last class. In the symmetrical fault, as the name says, there is only the positive sequence network or positive sequence models of the equipment that come into play. So, so essentially it is just so if this is a reference bus actually which has 0 potential, reference by the reference bus we mean 0 potential bus. It will be EA and Z1, which is the positive sequence impedance, and up to the point of the fault, and IA1 which will flow. So, IA1, which is the fault current, will be equal to EA upon Z1. That's the only. Z1 of course is the Thevenin equivalent. We will see with an example, maybe not in symmetrical faults, but with unsymmetrical faults, how we calculate the Thevenin equivalent. Now, for calculating the fault currents due to unsymmetrical faults, which are actually occur more frequently. In fact, if you see the unsymmetrical faults are the single line to ground fault, the double line fault, and the double line to ground fault. The symmetrical fault of course is the 3-phase fault or the triple line fault or triple line to ground. Since the fault is balanced, it does not matter whether the ground is there or no. But if you see, this accounts for about 70%, and these two maybe account for more than 20%, I mean close to 30%, and hardly any faults, maybe 1% or so, are three-phase faults. Three-phase faults are very rare because they usually occur as a result of some error. Some earthing conductor is left and the line is closed, or some tool is left on the bus bars by the staff or something like that. Whereas in the case of single line to ground or double line, these occur more frequently. This could occur due to something touching the conductor, or some tree touching the conductor, something like that. So, the probability of that occurring is much more. So, to study the types of faults, the single line, the double line and the double line to ground fault, we will start with our basic sequence component and the equations that we developed last time. We saw that VA1, the positive sequence, in the positive sequence network, the voltages are given by this. In the negative sequence, since there is no negative sequence generated voltage, this is simply IA2Z2, and VA0 is minus IA0Z0, since there is no negative sequence generated voltage as well. These Z1, Z2 and Z0 are the equivalent impedances, or the Thevenin equivalent impedances of the respective symmetrical component networks. Now, if we write this in a compact matrix form, it will take the form of VA0, VA1, VA2 is equal to I'm sorry. Okay. So, this is the basic equation which we will use for all our rather developing equations for all our faults. Okay. Now, we will take the case of solid faults. We are not considering any fault impedance to be in picture, actually, which means that ZF is equal to 0. We are taking a three-phase circuit, and in the case of the first fault, which is the SLG fault, we take that, say this is phase A, B and C, we take that phase A gets shorted to the ground and there is a solid fault, which means that and also one more assumption is, the first assumption of course is that there is no fault impedance. ZF is equal to 0, and the second is that the pre-fault load currents are zero, or there is no pre-fault load flow in that in this. Okay. Actually, if we want to do it in a more rigorous fashion, we will have to take the three lines and then take three impedances and switch them according to the nature of the fault. Okay. But we are simplifying things a bit for analysis. Okay. And then depending on the nature of the fault, close the switches and appropriately. These boxes represent the impedances, and depending on the nature of the fault, you can close the switches and get a proper matrix representation. But in this case, we are taking those ZFs to be 0, and or rather these individual impedances to be 0 and the pre-fault currents also to be 0, so that our analysis is simplified a bit. Now, going back to this, for a single line to ground fault, what condition we will get is VA is equal to 0 because phase A is solidly shorted to ground, and since there are no pre-fault load currents, IB is equal to 0 and IC is also equal to 0. Now, if we plug these three into our equation above, before that we will have to get the sequence components of the currents, so that we can plug it into our equation here, which we will use this equation here, which we will be using for all the faults. Okay. So, in this case we have IA 0, IA 1 and IA 2. We have studied this in the last lecture. A square A, and this is of course IA, IB and IC. Okay. But in our case this is 0 and this is also 0, okay, which gives us okay. So, if you see all the sequence currents are the same and they are equal to 1/3 of IA, which suggests a series connection of sequence networks. We will see that when we plug these values into our equation, matrix equation here as well. So, if we do that, what we will get is this VA 0, VA 1, VA 2 is equal to 0 EA 0, sorry, Z 0, and since all the currents are equal, we can write them as IA 1 itself. Now, if we add all the three rows together, that is pre-multiply both sides by 1, 1, 1, then what do we get? VA 0 plus VA 1 plus VA 2 is equal to, okay, I will write it in the proper sequence so that there is no confusion, minus Z 0 I 0 plus EA minus Z 1 IA 1 minus Z 2 IA 2. Okay. Now, what is VA 0 plus VA 1 plus VA 2? It is nothing but VA. Which in this case is equal to 0, as there is a solid short to the ground. So, otherwise this would be equal to ZF into IA 1. Okay. But in our case we are taking it equal to 0 to simplify things a bit. So, 0 is equal to EA, I am just collecting the terms, I am sorry, this is, all of this is IA 1, since we have represented it as IA 1 here. So, we are collecting the terms here, and then this is simply Z 0 plus Z 2, Z 1 plus Z 2. Okay. Which means that IA 1 is equal to EA upon Z 1 plus Z2 plus Z0. Okay. So, this is the equation that we will use for calculating the fault current. Okay. Now, what does it suggest? This one and as well as these that the fact that the sequence currents are equal suggests a series connection. So, for if this is your say reference bus for the positive sequence, what you will get is Z1, this is the reference bus for the negative sequence, this is Z2, this is the reference bus for 0 sequence, then you get Z0. Okay, and then this is connected to the and you have I1 flowing here. Okay. So, the one important fact that we need to consider here is for a 3-phase fault, what we have is, I am sorry, should have written it differently. For a 3-phase fault, what we have is I1 is equal to EA upon Z1. Okay. And for a single line to ground fault, what we have is IA1 is equal to EA upon Z1 plus Z2 plus Z0. Okay. The fault current actually is 3 times this, because remember fault current is actually IA, which is 3 IA0 or IA1. So, the fault current in this case would be 3 times this, and if you compare with this is the SLG fault, if you compare with this equation here, okay, then and say for this equation multiply and divide the numerator and denominator by 3, then the numerator here is same in both the equations is same, say equation 1 and 2 is the same. But if you look at the denominator in the 3-phase fault case, it is 3Z1, while in the case of a single line to ground, it is Z1 plus Z2 plus Z0. Now, usually what happens is Z1 and Z2 may be equal or are in most cases equal to each other, and Z0 if there is a extensive transmission line network is higher than the 2. So, if you compare these two, then you will see that the value of this number is, or this addition is higher. So, this denominator is higher, and that is why you will find that single phase fault current or SLG fault currents are usually lower than 3-phase fault currents. Three-phase fault. I said usually, it is not always the case. When you find that a single line to ground fault produces a larger current than a 3-phase fault, when this Z0 is very small as compared to Z1 and Z2. That is when this addition is smaller than 3Z1, and such a condition occurs very close to the generator, because if you remember for 3-phase generators, as we saw in the last class or last few classes, for 3-phase generator this value is very low. In fact, if you see theoretically it should be 0, but because of the fractional pitching of windings and all that, there is some 0 sequence impedance, which is some 0.1 to 0.5 or 0.7 times, or 10% to 70% of that of Z1. So, for a very close up fault to a generator, single line to ground currents can indeed be higher than 3-phase fault currents. Okay. Now, having said that, we will move on to the next fault, which is the line to line fault. Okay. This means line to line. To taking our three-phase circuit once again. This is not a circuit, just a representation ABC. We will take that there is a solid fault between phases B and C, since we are talking of line to line, which means say two phases are shorted. Here in just for the ease of analysis, we are taking B and C. It could be A and B or A and C as well. Okay. Since there is a solid fault between solid short between B and C, we have VB equal to VC and IB. Since the current is the same, IB is equal to minus IC, or IC is equal to minus IB, whichever way you choose. And since the pre-fault load flow load currents are 0, IA is equal to 0. So, we will use these 2 or 3 facts and modify our sequence components of voltage and current accordingly, and then plug it into our equation, which we said we will be using for all faults, which is this equation, or rather this equation. Okay. So, now moving ahead, for the voltages, we have VA0, VA1, VA2 equal to 1/3 of one A square, 1 A square A, and VC is equal to VB, so we can write this as VB as well. So, what this tells us is VA1 and VA2 are the same, or VA1 equal to VA2. So, we will use this. We will talk about VA0 a bit later. Okay. For the current, I am sorry, for the currents, writing the same in the form of symmetrical components, we have IA0 is 0, sorry, IA is 0, we can write this as IB and minus IB. So, what does this imply? That IA0 is equal to 0, okay. And what is IA1 and IA2? And what is IA2? Minus of A square IB plus AIB, which means IA1 equal to minus IA2, or minus IA2 equal to minus IA1. Okay. Now, since IA0 is equal to 0 and Z0 is some finite value, we have VA0 equal to 0. Okay. So, VA0 is equal to 0 and VA1 equal to VA2, which is what we have derived earlier. So, if we plug it into our matrix form, what we will get is this VA0, which is 0, then VA1, VA2, zero. Actually, VA1 equal to VA2, but we will utilize the fact later, minus Z0, 0, 0, 0, 0. Just clean this. IA0 is 0 as we have derived earlier. IA1 and minus IA1 because IA2 is equal to minus IA1. Okay. Now we can simply do this operation mathematically, pre-multiply both sides by this, or in other words, in plain words, if we say we are doing row 2 minus row 3. Row 1 is anyway equating to 0, so it does not matter here. So, if we do 2 minus 3, we will get VA1 minus VA2 which are equal. So, it is 0 is equal to EA minus Z1 IA1, and this is we are doing minus of minus. So, we will get the same thing again is Z2 IA1. Okay. And since this is equal to 0, so we have 0 equal to Z1 plus Z2 into IA1. So, we have IA1 equal to EA upon Z1 plus Z2. Okay. What does this suggest? In the last kind of fault or the last type of fault, we got a series connection. This suggests since IA1 equal to minus IA2 or IA2 equal to minus IA1, this suggests a connection, a parallel connection. Z1 and Z2. So, whenever we have a line to line fault or we need to analyze a line to line fault, this is the kind of a circuit that we will use. Okay. Now, we will go on to the final type of fault, which is the line to line to ground fault or double line to ground fault as it is commonly known. Okay. The representation of this fault in our format is this. These are the 3 phases. We will take the same 2 phases again, B and C, but unlike last time, now there is a solid fault to ground. Okay, they are grounded. In which case, now we have VB equal to VC, and since it is a solid fault, is equal to 0. Also, the earlier condition. Earlier we had only VB equal to VC, but now in this case it is equal to 0, and IA is equal to 0 since there are no pre-fault currents flowing in the circuit. Okay, so now we will substitute this in our to get our symmetrical components voltages. One third of 1 A square and 1 A square A. And now what do we have? We have VA here, and VB and VC are both 0. Okay. So, what do we get? All the 3 sequence components are equal, is equal to 1/3 VA. Okay. In the single line earlier in the single line to ground fault, we got the 3 sequence currents to be equal. Okay. Now, now we will write our equation once again, just to refresh our memories, and since we will need to, this fault involves a bit of a slightly more manipulation than the earlier two. So, just to make it a bit simpler, we will write this again, the matrix form which we are using for all our faults. Now what we will do here is, since all the three voltages are or sequence voltages are equal, what we will do is we will substitute VA1 value for all of them. Okay. So, here all these three values we will substitute with this. Okay. Once we have done that, we will we will pre-multiply both sides by Z inverse. Now, what is Z inverse? Since this is a diagonal matrix, I am sorry, it is not Z equal to 1, it is Z inverse. So, we will pre-multiply both sides of this matrix equation by Z inverse, which is nothing but, this is, if we consider this matrix as Z, Z inverse, since it is a diagonal matrix, what is Z inverse equal to? It is quite simple, just Z0 1 upon Z1 . So, we will pre-multiply both sides of this equation. We will first step is substituting EA minus IA1 Z1 here for all the three values, since they are equal, and then pre-multiplying both sides of the above equation by Z inverse. Okay. So, what we get is 1 by Z 0 0 0 0 1 by 0 0 0 . Since this is this vector here, so we are simply substituting it. This is this Z inverse is, we pre-multiply on both sides. So, there is a one more term which is minus. Since there was a Z associated with this, Z into Z inverse will give us an identity. Okay. Now, what we will do is, we will pre-multiply both sides by this vector. Okay. That is, add the three rows together. Okay. So, what will we get here in this case? If we do the addition, we will get EA, this is the first term. So, we will get EA, we are multiplying and adding the three rows together. So, EA by Z0 minus IA1 Z1 upon Z0 plus EA by Z1 minus IA1 plus EA by Z2 minus IA1 Z1 by Z2 is equal to EA1 by Z1. What happens to this row here is, since IA is equal to 0, IA0 plus IA1 plus IA2, we will get here one term of II0 plus II1 plus II2, which is 0. Okay. So, now if just collect the terms together, I1 into 1 plus Z1 by Z0 plus Z1 by Z2 is equal to EA into okay. So, IA1 in this case is equal to EA upon Z2 plus Z0 upon Z1 Z2 plus Z1 Z0, we just opening out the terms and multiplying, plus Z2 Z0. So, we will just quickly do some manipulation here. We will get Z1 out. What we will do is divide the numerator and denominator by Z2 plus Z0, which will leave us with A upon Z1 plus Z2 Z0 upon Z2 plus Z0. So, what is this term Z2 Z0 upon Z2 plus Z0? It is nothing but Z2 parallel with Z0. Okay. So, what does this suggest? This suggests a connection like this, a parallel connection like this. What we have is EA Z1 okay. So, this is what we will use when we do a double line to ground fault calculation. Okay. So, now we will look at a problem, quickly look at a problem before we maybe a couple of problems, so that the concepts are clear. We will maybe start the problem today and then continue in the next lecture. So, I will just introduce the problem and then we will look at the solution in the next class. Okay. So, this is a problem taken from a book by J. Lewis Blackburn, and it is symmetrical components for power systems. There are a lot of unsolved problems at the end. So, we have taken one unsolved problem from the end here, and this is the problem. So, this is a single generator connected to the system. This is the system here, the equivalent source. The transformers etc. are given, the values are given. We will just quickly look at the value at the problem, so that we do not have to repeat the whole thing next time before we stop here. Okay. So, this is the generator. Here this transformer is star grounded and delta on the generator side. This is also a delta on the system side. Okay. And I will write the problem. This is the source or equivalent source, and here this is the bus G, this is the bus H, and here x1 equal to x2 equal to 0.1 pu. For this transformer here, X is 0.05 pu or 5% leakage impedance. Okay, this is since this is an American book, so that the voltages may seem a bit unfamiliar. There they use 115 kV instead of the 132 or 110 kV that we use here in India. So this, for this line, x1 equal to x2 is equal to 0.3, and you notice here that the x0 is quite high, which is 1. Both are in pu. Okay. For this transformer X, the per unit leakage impedance is 0.1 pu, and for this generator here, I will write it down here. For the generator on the right hand side, x1 equal to x2 equal to 0.24 per unit. Okay, and what is the problem? Calculate the line to ground faults at buses. This is the first part of the problem. Calculate the line to ground G and H and M, which is the midpoint of the line. Okay. So we will quickly draw the symmetrical component networks rather, and then we will stop for today. We will not do the calculation. So the positive sequence network for this is for a fault at bus G. So this is EA. We can take it as 1 pu here. So we will just write 1 pu. Then the generator positive sequence impedance is 0.1. Sorry, not 1.1. Okay. Then there is a transformer between that and G. This is the G bus. So this transformer is 0.05. If you keep this diagram in front of you, then we have the line 0.3. Then we have the bus H. Then we have the transformer with 0.1. This is also, we can take it as 1 pu, and we can assume it as 1 pu, and the system impedance is 0.24 pu. Okay. Now the negative sequence will be the same, except for the fact that you can just connect this to the negative sequence source, except for the fact that there are no voltages here in this case. So this will be 0.1. H 0.5, 0.3. I'm sorry, this is G, and this is H, 0.1 and 0.24. All are in per unit. I am not writing that it is in per unit. Now the zero sequence, for the zero sequence it will be slightly different. And you need to be careful, because the vector group of the transformers also has to be taken into account. So all that we learnt over the past few classes we will use in this calculation here. Okay. Since this is a delta star grounded transformer, what will happen is, I am sorry, should have done this. Is that it will get grounded here, or I could have drawn this as a solid ground line and written the transformer impedance here. G, this is 1, this is H, this transformer is 0.1, this also goes to the ground. Oh, one interesting thing is the zero sequence of this is not mentioned, of the source, either the source or the generator is not mentioned here in our problem. I have mistakenly taken this as 0.1, but it is not mentioned, and nor does it matter in our case. Why? Because this is a delta star transformer, and zero sequence currents can't flow in the lines of the delta. So, these 2 points remain open. So, it is connected like this, and since they are open, the value of this or this does not matter. So, that is why even though the values are not given in the problem, they will not affect the results. Okay. So, we will stop here now, and we will continue with the calculations of this problem and another problem the next time. Thank you.